Okay. Yeah. I wonder if you can do this.
Okay, sorry. So project number 1 is due on Friday at noon. We will finish chapter 2, part 1 today, and start part 2. Are there any questions?
Are you going to review a little bit of what we went over last time?
Like 20 seconds of it. Do you have a specific question that you would like to ask?
Like review the Z star formula
Okay.
and what each of those exactly are. I think I got it, but
So I think maybe perhaps an area of confusion was in what the way that I originally wrote out Z star was I didn't necessarily put a subscript R. And so it's kind of hard sometimes to know exactly what needs to be calculated for every single resample. So Z star R sub R is equal to T star sub R minus T over then this variance calculated on a particular resample, take the square root of that variance. So, for example, let's just say, well, let's say that T is equal to Y bar. Then the variance of Y bar, which is sigma squared divided by N, estimated variance of Y bar is sigma squared divided by N, the hat on sigma squared. So then, this would be V. Then the Z star here would be Y bar star minus Y bar all over the square root of sigma hat squared star divided by N. So what that sigma hat star notation means is that, again, for every single resample, R there, we have to calculate a regular old variance. The variance of the Y stars. And so that denominator gets changed for every single resample. Is that help at all?
yeah.
Okay. And I mean, getting this V star is often the more difficult part. In the parametric case, it's not too bad because you have a way to actually derive V, which I think was a topic of the conversation. Perhaps that was part of the cert post. I don't, maybe not. But I've been asked that by a number of students. Well, what do I use for V for the parametric bootstrap? Well, it simply comes from the parametric assumptions. Then V star is just kind of a plug-in estimate. So I'll just plug in with the corresponding stuff with B now with respect to the samples. Now for a non-parametric bootstrap, the question is now you don't have a quick and easy way to get V. Now there are some simple derivations that can be done that don't rely on distributions at all for simple statistics. But for more complicated statistics, like we were talking about coefficient of variation, what do you use? And so what one could use is come up with then the asymptotic variance and use that then for your V and then calculate the corresponding quantity for V star. In section 2.7, we will learn about, I think, 4 different other ways to come up with V star. Any other questions? Okay. So we were talking about the boot.ci function, which helps automate the process of doing some of these confidence intervals, but you need to be very careful about the structure of the stuff that you pass into boot.ci, along with what is actually being, knowing what's actually being calculated. And so last time we talked about some of the issues involved with that, and in particular we wanted to match what we calculate, let's say, without the boot.ci function, say almost like by hand, with what the boot.ci does. And when I was first teaching this course in 2006, I was having problems trying to duplicate what boot.ci actually did without using boot.ci. I think I mentioned this to you. And so what I want to briefly talk about is how that I figured out what boot.ci does. And the reason why this is important is because in this class, but in particular outside of this class, you're going to be left with situations where, you're trying to figure out what R is doing. Well, what's the process that one would go to do that? And so I think, not just in this class, but I think even outside this class, this brief discussion will be helpful. Okay, so we left off on page 271. And I mentioned this a little bit, I think, already. And that is, the first thing you should do is when you're not for sure, why are my calculations different from, in this case, the boot.ci function in comparison to what I was doing without the boot.ci function, even though they should be exactly the same. Well, the first thing that you can do is actually look at the function itself. And we discussed how to do that. Just simply type boot.ci your command prompt, and this is what the boot.ci function looks like. I think in particular we talked about, well, what's it using for the variance in terms of V and V star? Where is it finding this? Now, if you remember the way that boot.res, if this is the results from boot, how that's structured, $T0 corresponds to the statistics that are calculated from, let's say, calc.t. And typically the way that we're going to formulate this is so that the first statistic is always going to be the statistic of interest, let's call it T. Actually, we use kind of R pseudocode. Will always be T, and then the second thing that's coming back is V. So in order to know that boot.ci actually picks the variance correctly out of boot.res $T0 and also boot.res $T, you need to know what's going on. And the key portion of the code is right here. Without going to all the details, it's a little more complicated than what I'm describing right now. Basically what happens is that boot.ci picks out the second element of the thing that's returned by calc.t. There's an index argument up here, and that corresponds to what will be by default 1:2. So 1 and 2. But then I wanted to see the actual way the interval is calculated. I want to see the actual formula, like what I presented in class. So you can page through the function code, and eventually you come down to here. Now, one thing that I think our programmers could do a much better job at is commenting their code. So often when you just type a particular function at the command prompt in R, there are no comments at all. Why? Well, because the author will say, well, you can just simply run the code line by line and figure out what it's doing. Well, yeah, but it sure would be nice to have some comments. And so, you look throughout this code for boot.ci, you don't see anything where it says, where's the student i's confidence interval being calculated? Now, I hypothesize that most likely it's calculated right here because you have something called student equal stud.ci, and then some stuff inside it. It makes sense that's where it would be. If you look throughout, there's really nothing else there that would lead you to believe it's being calculated anywhere else. So what this is basically telling me is that there is now a function out there called student.ci that calculates the interval. So there's another function out there. I should be able to just simply type, make this a little bigger. It's too big. I should simply be able to type stud.ci and see the function. And I've shown this to you once before that stuff like this can happen. Does anyone remember what one does? Yep. There's a function called getAnywhere. And that shows me now the actual code. Now back in 2006, I did not know that that function actually existed. And so I was struggling, where is it? And because previously, well, what I had noticed about 1 or 2 years prior is that when I would type a function in R, it wouldn't always come back to me with the code. And I guess I must have missed some of the release notes for future editions of R where they say now certain functions are hidden to the user. Well, how do you see it? That was never obvious to me. So what should you do next? If you have a question about something regarding R, well, the first thing that you can do is go to the mailing list archive, and you could search for some keywords. Another thing you could do is go to Stack Overflow. Those were 2 things that I showed you during the first week of class, I believe. And so I searched the archives. I could not find anybody else who had exactly the same question as me. So then what? Well, post something to the listserv. So that's what I did. And here is my message. This was Saturday, January 7th, 2006. So I tried to, as briefly as possible, say what my problem was. I couldn't find boot.ci. I made sure to mention that I looked elsewhere for it, or tried other ways to find the solution to my question. So I posted it there. That same day, I got 2 replies, including one from Brian Ripley. Who's Brian Ripley? Here's what's called the R core group. These are the people that control the main source of R, like the stat package, graphics package, all that stuff. Brian Ripley is one of those. Let's cut off there. He is one of the people in the R core group. So it's nice that we were both working on a Saturday. In fact, it was probably more of a Saturday night for him. This is out in Cambridge. I could be wrong. In England. And anyway, so he replied, and he said, "Here you go. Get anywhere." So that was nice of him. But please make sure that when you do post something to the listserv, if you ever do that, make sure you try to explain your question very good, and you tell people that you tried to find the answer and you couldn't, because otherwise you may get a not nice reply. Brian Ripley's known for not giving not nice replies, and so I was quite happy that he gave me a nice reply. Anyway, that's getting more into the story than what you would like, but that's how I did. So that's how I found the answer. And that's how you solve problems like this in R where you're not for sure what's going on. So now I have this function. I can see it now. And again, without going into all the details of the code, you could execute this line by line if you wanted to. We see that Z, like in our notation, is calculated. Kind of looks somewhat familiar to what we're used to seeing. Well, what about these quantiles from this Z star distribution? Well, we have something called QQ here, quantile. So you need basically 2 quantiles. QQ for 2 quantiles. And notice what it does. I was surprised when I saw this. It doesn't use the quantile function itself, like what we use. Instead, it uses the norm.inter function. You want to know what that stands without looking at the notes. Normal interpolation. You've heard of interpolation, probably in other classes before. And basically, this function then gives me my corresponding quantiles that I need. So you see conf there, conf corresponds to that by default, or is passed in from the boot.ci function. But well, what does norm.intr do? Well, again, you can look at the function and see exactly what it's doing. I'm not going to show that here to you, but basically what it does is it will return the same answer that we would get from the quantile function if, let's say, if r plus 1 times alpha is an integer. So let's say r was 999, alpha was 0.025. Then that means return back, let's say, the 25th order value of c star. But let's say instead r was, let's say, 1,000. So that means 1,001 times 0.025 is not an integer. Well, what do you do? Well, in our book, based upon its definition of what a quantile is, it would still take the 25th ordered value. That's why we use the type equal 1 argument for quantile. However, what they do in this function is they actually interpolate between the 25th and the 26th largest value, and that's how they would come up with the interval, or the quantile, and thus then eventually the interval. So, as I spent a few hours trying to figure out what was going on wrong, you can actually get a different answer from boot.ci than you could if you actually used the exact formulas that were in our book. There are going to be very, very, very small differences, but that interpolation can happen there if r plus 1 times alpha is not an integer. Okay. Any questions for that long explanation of something that's quite minor in some respect, but can be quite frustrating too? But it's also, sorry for those of you who like SAS, but this also leads you to realize that stuff like this goes on in the background of other statistical software too. But you're not really left with an ability to figure it out in SAS and see exactly what's going on. You can't. Sure, you're going to have documentation, but that's not going to give you the necessarily exactly what's going on. So, it's one of the nice things, I guess, about R as well. Okay. Lastly now, if you remember the boot.ci output, do a split screen. There was another interval calculator, something called normal. Well, what is this interval exactly? Let's talk about that. Okay. Well, let's say that I have some statistic, and it has an approximate normal distribution where the mean is theta plus beta, where beta is the bias. Theta is our parameter of interest. So we have a perhaps biased statistic t. The variance is sigma squared. So in other words, this means that t minus beta, this approximate normal distribution, mean theta, variance sigma squared. So with that as a background then, what one could do, similar to what we did before, is take the alpha quantile from a standard normal that's less than t minus beta minus theta divided by sigma. It's less than z1 minus alpha. That's approximately 1 minus 2 alpha, right? All we're doing is acknowledging the fact that we might have a biased statistic. then you could use some algebra, and so you just have theta in the middle, and then from that I'll substitute the observed values for your random variables to get this as a confidence interval. Observed value t minus, this is the bootstrap estimate of the bias, because otherwise you wouldn't be able to calculate it without the bootstrap. I guess unless you were doing a parametric bootstrap. Or parametrics. Okay. Here's your quantile from the standard normal, and there's V. Well, that would be then the estimate of 6. So we've already talked about how to actually calculate V. I'm not going to go through the details again, but all it is again, a bootstrap estimate of the bias. Now, if you were to use the boot.ci function, and let's say set type equal norm only, and let's say calc.t only had one element in it, return to the user your t, so no variance at all, then R will, for V, substitute a bootstrap estimate for V into the formula that you see back here. If instead calc.t actually gave you back 2 elements, t and then V, boot.ci by default will put the observed value of that second element in there for V. So just to show you how this works. So based upon the stuff that we were doing before with the air conditioning data set, so I have the results in boot.res. I can find my bootstrap estimate of the bias, it's negative 0.915. I can find my lower bound for my interval as t minus beta, my 0.975 quantile from a standard normal, times the standard deviation of all the t stars. That's going to be my lower bound. My upper bound is found in a similar way. And here is my corresponding interval. This reproduces exactly what this particular boot.ci function does. Now you'll note that the output that was given earlier, this is page 71, has a little bit of a different value for its interval. And the reason is just simply what's using for V. So remember how we're actually having a second element in calc.t. So
It's not happening. There's that's right.
note that there is one error with tablet PCs that has never been solved in the 10 years that they've existed. I've used them for 9 years. I've always had this problem. Whenever you have a split screen like this, sometimes, you know, when you, let's say, as you can see here, when I circle this, and then if I come down here and circle something else, the circling disappears in the previous screen. What I'm really looking forward to is Microsoft's new version of the tablet. I think it's called Surface. It's supposed to come out later this year to compete with iPad and all those other ones. And it looks nice and allows you to use a pen and like iPad. Supposedly Steve Jobs doesn't think that people would ever want to use a pen. I believe I actually read that. So that's why it was just finger-based. But of course, you know, if I wanted to with my tablet PC, I could use my pen, or I can use my finger here and do stuff too. So all this actually existed since 2002, but Steve Jobs made it to make people interested.
Pretty.
Okay, that's the end of chapter 2, or chapter 2 part 1. So I said chapter 2 is the longest chapter because it really sets us up for everything else. I think once we get through all of chapter 2, things will move a little bit more quickly because then we have the basic underpinnings of what the bootstrap is, and then we can talk about, okay, now what happens if I want to do this? Well, it's just a slight modification of what we're doing. Okay. So, sections 2.5 and 2.6 are somewhat hard for me to actually cover in a course like this because it does really require having an understanding of what asymptotic statistics is all about. So what I will do is, hit the high points. I'm never going to ask you to prove a particular asymptotic result. Rather, what you need to know is how to interpret the final result in the end. And I will also give you some more references if you want to know more about the actual asymptotic underpinnings of the bootstrap and how that works. Okay. So, section 2.5 talks about sources of, let's say, error that can go around error in using the bootstrap. In terms of, there's two sources, simulation error and statistical error. Let's talk about simulation error first. We are essentially doing Monte Carlo simulations. So, because of that, you're going to have some simulation error unless you could somehow take, in our case, an infinite number of resamples, or I guess, what is it, 2n minus 1 choose n minus 1 different resamples, which is very difficult to do unless you have a very small data set. So, how large an error should you take? How large of an R should you take in order to feel good about yourself, that things are going to work out as you, had intended? And, there's not a simple answer to the question. We've looked at some examples before with respect to estimating quantiles, and we can see that as R gets to a certain point, now the quantiles aren't changing a whole lot. Well, that's a good sign that, you've chosen a large enough R. Just some very simple recommendations then. If computation time is short on the computer, take a large R. It's as simple as that. The R, let me just emphasize this, the number of resamples that they take in the book is typically smaller than what you would normally want to use nowadays. Computers have sped up in the 15 years since about this book was written. When I was preparing for class today, I was thinking, well, when I was first learning this stuff, what kind of computer was I using? I bought my first computer back in the late 1990s, and it was a 233 megahertz computer, 64 megabytes of RAM. I remember when I bought that computer, a good friend of mine who was also a student said, "What are you going to do with 64 megabytes of RAM?" Anyway, we got a nice monitor, I think it was a 17-inch monitor. That was extravagant. It cost me like $500. All total, my computer cost me like $2,500. It's quite an investment for a graduate student. I still have the computer too. It's sitting in my basement because I just can't get rid of it because I know how much money I spent on. My wife isn't very happy about me not getting rid of it, but anyway, it's down there. And my computer here is 2.4 gigahertz computer with 8 gigabytes of RAM. Also has it's a very small hard drive. It's a 130 gigabyte hard drive. My computer back in 1997 had a 4 gigabyte hard drive, which was kind of big at the time. So you can see how things have changed. And so to put it in the context of when this book was written, we can do better now. Take a larger R if you can. When estimating the extreme quantiles then of the distribution of t or t minus theta, you do need to take usually a larger value of R. And we've kind of discussed why before. Let's say that you're interested in the alpha equal 0.01 quantile from a distribution G. And if you take only 99 resamples, what does that mean for you? Well, you're basically taking the first order, let's say T star. And if you have a left skewed distribution, it's not going to be probably a good estimate. So, when estimating the center of G, typically you can get away with a lot less because you have a lot of information in the center of your distribution. Chapter 9, and I hope to do this. I have never done this section in this course before, so I hope to do this. And that is, Chapter 9 talks about ways that you can get away from taking a large number of resamples but still have good accuracy. Now you might be thinking, I just told you, well, just take a larger R because you have faster computers. But if the computation that you're taking, the computation that you're doing in, let's say, your calc.t function takes a long time, or let's say you are doing a Monte Carlo simulation to evaluate a statistical method that uses the bootstrap, so in essence you're using a simulation within a simulation, then you have time considerations to worry about. And so some of these methods, like the one that we'll talk about in Chapter 9, can be helpful. Also, and I hope to do this too, and this will be at the end of the course with this Chapter 9 stuff. Also, just recently, in the last, I think, 2 years with R, it's become a lot easier to do parallel processing. And what that basically means is, let's briefly talk about it. Well, someone tell me what parallel processing is. Anyone know? Okay. Essentially, it's this. I'll put it into our bootstrap context. Let's say I want to take 999, let's make 1,000 resamples. Well, how about I take 200 resamples on one computer, take 200 samples on another computer, take 200 samples on another computer, and go all the way up to the 5th computer. Ideally, your whole process is going to take 1/5 the amount of time, right? That's called parallel processing. Now, starting about we've been able to do parallel processing in R for some time, but there's been some recent innovations in R that make it a lot easier for people to use without necessarily knowing how to put stuff on this computer, how to put stuff in that computer, how to put stuff in that computer. And in fact, I think starting with version 2.14.1 in R, I think we're up to 2.15.1 right now, there is an argument in the boot function that allows you to do parallel processing. The problem is, I think in order to implement it, I need to check on this more. I think you need to be on basically a Unix-based computer, not a Windows-based computer. Hopefully, at the end of the course, I will take some time to talk about this in greater details because I think this is one of the really revolutions in statistics that we have now available to us is easy use of parallel processing. And one other little brief note. Now you might be thinking, well, geez, how are you going to be able to call this computer, that computer, that computer, that computer, and so on? Well, actually, most computers nowadays have multiple cores to them. So you can do parallel processing basically on your computer. For example, this has 2 cores. I have a 6-core computer in my office. 6-core computer in my office. And so that also takes away a lot of the extra stuff that you would have needed to know years ago. You would more easily do it. Okay. Now, when you read this section, again, there's going to be some stuff that's going to be hard to read. Make sure that when you see an equal with a dot on top of it, to say, let's say, t equal dot something. Again, what this basically means, you can interpret this to mean approximate. What this might actually rely on is some asymptotic approximation. That's all. I also give some other notes too to help you read certain parts here, and I'll let you look at those on your own. So, one source of error is simulation error, and we can usually take care of that by taking a large enough R. Well, what about the statistical error, though? And what that means is that, again, we're using f hat to estimate f. Now, ideally, we would like to know what f is. Well, let's use f hat. That's a simple thing to do, but of course f hat's not going to be a perfect estimate of f. So because of that, we have some statistical error that we have to worry about. So I guess regarding this statistical error then, when is the bootstrap going to work the best, meaning the lowest amount of statistical error? Well, it's given in 1 here. The best bootstrap estimates result from the parametric bootstrap when the correct model for f is used. That makes sense. You know what f is. You're using the correct f to begin with. Well, great. But, and so you might be thinking, geez, I'm going to use a parametric bootstrap from now on. Well, the worst bootstrap estimates result from using the parametric bootstrap with the incorrect model for f. Of course, you're left with the question always in the back of your mind whenever you do a parametric bootstrap, is my version of f correct or not? So, what you're left with then? Well, then the non-parametric bootstrap, and that generally will typically always be good. Not as good as using the parametric bootstrap with the correct f, but generally it will be good. Okay. Well, a particular way then that you can also reduce then the statistical error is to use a particular kind of statistic. We touched on this a little bit in the last section. And that is, ideally what we like to be able to do is use a statistic, let's call it Q, which is let's say a function of T, our real statistic of interest. Choose a statistic Q that is pivotal, or approximately pivotal. And we saw the benefits of doing that when we looked at that the parametric bootstrap confidence interval. We saw how we got the exact confidence interval from using the parametric bootstrap. And it ended up being because we were using this pivotal statistic. So why is using a pivotal statistic good? Well, distribution is not dependent upon the parameter. So there's less things that you have to estimate, thus less chances for error. Less chances of getting that f wrong. So let's take a look at a little example here to help emphasize the point. Earlier we worked with this. Y bar divided by mu was gamma n1, a pivotal statistic. So suppose I take a large number of samples from f where mu is equal to, let's call it mu1, and let's put 1 here. And I calculate y bar divided by mu every single time. And let's say I plot my data that I get from my sample. So here's mu1, here's my y bar divided by mu, and I plot this right here. Suppose that I take a different value of mu. Let's call it mu2. What do you think that, and then I take y bar divided by mu2. What do you think that plot's going to look like approximately? About the same, because I have a pivotal statistic. And in fact, it doesn't matter what the value of mu then ends up being, is that you're still going to have approximately the same. And that's the beauty of a pivotal statistic. It's not dependent upon any unknowns. So now apply this to the setting where you are now using the bootstrap. So instead of y bar divided by mu, you're going to use y bar star divided by y bar. What's your plot going to look like? Like that. And that's why working with pivotal statistics is nice. But then the problem is, well, first of all, that's great in a parametric setting, but what do you do in a non-parametric setting? We discussed this a little bit earlier. You can't really say something's pivotal necessarily in a non-parametric setting, because what's the distribution of t? So what we thought was, well, what one could do with like the studentized bootstrap confidence interval, take something that kind of looks like a pivotal quantity that we would normally do maybe in other applications. Take t minus theta over square root of v. And that was the idea behind the studentized bootstrap confidence interval. It's not a perfect idea, but it all works well in a lot of problems. But here's another thing that you could do, is how about we get an asymptotic pivotal quantity? Note that this doesn't say anything really about the distribution of f itself, because you're relying on asymptotics. And if I can get an asymptotic pivotal quantity. Maybe I use this as my Q for what I calculate for every single bootstrap resample. Well, it's not going to be pivotal exactly, but at least you know for a large sample size it's going to be pivotal, so it seems to make better sense to use that than something that you know is probably not pivotal to begin with. So let's talk about asymptotic pivotal quantities. First of all, just to help me background, I know you guys, step 980 you took. Did you talk about a variance stabilizing transformation in your course? How to find asymptotic? Okay. So this will be new to everyone. So often we're left with situations such as this. We have a particular statistic of interest, t, estimating theta, and square root of n times t minus theta converges the distribution to some random variable x. Typically it has a normal distribution. There are cases where it's not actually normal, but some normal distribution. And let's say that that normal distribution is represented this way. X is distributed normal 0 k of theta. So the 0 there means that t is asymptotically unbiased. The k of theta there means I have a variance, and it's dependent upon my parameter of interest. That's not good, as you'll soon see. I guess. Yeah, I'll just leave it at that. So if we do the same, so, again, similar to what we've done before, one could show, this quantity here we can find this probability is about 1 minus 2 times alpha, because we have a normal distribution. Do some algebra, and then eventually get down to here, a confidence interval for theta. But what's the problem with this particular confidence interval, though? The left and the right-hand sides depend upon theta. But you want theta only to be in the middle. So you have a hard time then actually calculating this interval then. Well, here's an example of that you're all familiar with, where something like this happens. And we'll talk about the actual solution, or one solution, and we'll talk about a better solution later. Let's say that I have a population proportion. Let's call it pi that I want to estimate. So perhaps pi is the proportion of successes for some experiment. And let's say I'm going to estimate it with the estimated proportion. In other words, the number of successes I observe in a sample divided by my sample size. Call that P. So P estimates pi. Hopefully it's familiar to those of you who took my 875 course. If I look at the random variable version of this estimated proportion, capital P, one could show, it's a standard result you often see in asymptotics course, square root of n times P minus pi converges the distribution to a normal random variable, mean 0, and variance pi times 1 minus pi. How does one actually do that? Just for background, it's just essential limit theorem result. The reason being is because this P is a sum of, you could say, Bernoulli random variables, zeros and ones. Take the mean, so take the sum, divide by n. It's just basically essential limit theorem. So notice how this, you could say this is, let's say, k of pi. It's a function of your unknown parameter. One could then do some algebra and calculate or come up with this particular interval. The problem with this interval for pi is that pi is also on the left and the right-hand side. So what does one usually do in this kind of situation to get rid of this? Replace them with p's. And this is what's often referred to as a walled confidence interval for pi. And for those of you who've had my 875 course, how well does this interval work? It doesn't work very well at all. Please don't ever use this interval in practice, even though you might teach it. It's a very bad interval. So what I mean by bad is I'm talking about the confidence level. So you might say it's 95% confidence. You might have a 95% confidence interval, but in fact it might be 85%, even more. So what can we do in these kinds of situations then, in general? Well, all of you indicated to me that you know what the delta method is at least a little bit. It's in the cell and burger. And what we can do is this. The square root of n times some function of t, it's called h of t, minus h of theta converges in distribution to a random variable x that's multiplied now by h dot of theta. That dot there is a common way that people use to indicate derivatives. That's a little bit more compact. Okay? So the derivative of h of theta with respect to theta. So what that means then in a general setting when x has a normal distribution, of course, let's say that I have x that has a normal distribution. Let's say normal 0 sigma squared. If I take 3 times x, then that means it's normal what? 0, 9 sigma squared, right? So in this particular setting, this h dot of theta is then squared, and so that h dot of theta times x has a normal distribution with mean 0, variance of h dot of theta squared times k of theta. This is just a regular old delta method result. The reason why this is important then is that, notice I haven't said what this function h is. How about we actually choose a particular function h such that that theta that we had over here ends up disappearing, ends up being canceled out by a theta that ends up being here. So that in the end I have a variance that's no longer a function of theta, it's constant. This is what's called a variance stabilizing transformation, the choice of h. Very common technique that's used in statistics. So that in the end, what I want is that this variance to be a constant. Let's call it c. Typically, c is chosen to be 1 because it's easy. And then you get a same result. So what do I choose, though, for this h of theta? It's actually quite simple. So I have c squared is equal to the derivative of h of theta squared times k of theta. Okay? I want to solve for h of theta. So how about we take this? How about we move this k of theta over to this side, to be divided by k of theta. I take the square root of both sides, and I'm left with h dot of theta is equal to c over the square root of k of theta. Let's get rid of that derivative by taking integral of both sides, and that's how you find h. So, going back to this confidence interval for pi example, we had that problem of pi being in our variance. So how can I get rid of it? Well, k of theta was equivalently pi times 1 minus pi. So I could take the integral of 1 over the square root of that. And going back to your calc 2 days, you could find that this is equal to 2 arc sine square root of theta. Sorry, square root of pi. What that means then for us is that if I take square root of n, h of t minus h of theta, that equivalence, then I plug in my arc sine there with the square root of p. Now I get a standard normal random variable or convergent distribution. So again, the arc sine transformation with the square root there is the variance stabilizing transformation that one would use when trying to estimate a population proportion. Then in general, what's your interval for, let's say, h of theta? Well, do the same thing that we've done before. H of t minus the quantity from the normal distribution times then the square root of the variance. Well, what's the variance? 1 over n. Don't forget about the n, the n itself. Make sure you understand where the n comes from. So that's the interval for h of theta. Of course, though, we're really interested in theta itself, so what do? Use the inverse transformation. And there is your interval for theta. With respect to the interval for pi, here's my interval for arc sine square root of pi. And then what one could do is apply the sine transformation to both sides, also with the square, and you get the interval for pi itself. This is referred to often as the arc sine interval for pi. Very common transformation. It works much better than the walled confidence interval for pi itself. For those of you who have my 875 course, I don't usually talk about this interval because it was better than that. Okay, so it's a very common technique to use in statistics. It's a useful thing to put in your lesson, your statistical toolbox. Just to remind you, the reason why we went through this is because there are going to be times where we need some kind of pivotal quantity to work with, and it's not going to be obvious what to work with. And so this little technique gives us an asymptotically pivotal quantity that we could use. You want to know more about variance stabilizing transformations? There's 4 references in order of my preference. These first 2 books are excellent books on asymptotics. In particular, Ferguson, that's the one I use for, I had a 2-semester sequence when I was in school. This is the one that we use. What's great about this book, even though it's 15 years old, it's so widely used, what's great about it is that all the exercises are worked out in the back, which is nice. These other 2 are harder reads. Okay. And again, the reason why we're interested in these pivotal quantities is because to put it into other terms, it's going to help us get, let's say, perhaps confidence intervals that are closer to the true confidence levels. Oh, I'm sorry. True confidence levels are closer to the stated levels. Okay, so page 10. Statistical issues. Interesting title for a section. Now, when you do statistical research, you're going to develop a statistic, perhaps. You're going to need to evaluate that statistic. Depending upon the situation, but most of the time, what you're going to need to do is you're going to need to determine, well, what's the sampling distribution for your statistic. You're going to need to determine the sampling. Let's say that you have somehow figured out what the sampling distribution is for the statistic. Maybe you've proved asymptotically what the distribution is. Maybe you've actually derived it, assuming some underlying distribution for, let's say, your y's, or maybe you're using the bootstrap. Well, you're going to need to be able to prove that indeed this distribution and what you're trying to do with it works. How do you do that? There are typically 2 different ways. You're going to examine the procedure asymptotically to see how it goes from n to infinity, so in essence, the asymptotic distribution. Or you're going to examine its properties via Monte Carlo simulation. You pick up any kind of issue of JASA, I would say maybe 75% of the papers at least will have this in there. Maybe at least 50% of the papers will have this in there. Often they have one. Give you some perspective about how important this is. So what this section of the book, though, focuses on is evaluating the bootstrap in an asymptotic sense. And here's a very, very good quote from our authors of our book to describe what they are interested in doing in this section and why they are interested in doing it, and also the problems with doing it as well. So let me just simply read this to you. Under what idealized conditions will a resampling procedure produce results that are in some sense mathematically correct? How do you define mathematically correct? Often people say as n goes to infinity, you get what you expect. Now, answers to questions of this sort involve an asymptotic framework in which the sample size n goes to infinity. Although such asymptotics are ultimately intended to guide practical work, of course, when do you ever have a sample size of infinity? I've never had one. They often act as a backstop by removing from consideration procedures that do not have an appropriate large sample property. So, in other words, we like the stuff to work well for a very large sample size. Of course, you're never going to have a sample size of infinity. So this serves as a way to say, let's throw out the other procedures that as n goes to infinity, it just doesn't work good. Also, I'm not going to read the rest of it, but also it's important to know when the bootstrap will fail. And the bootstrap is not perfect. It can't solve every problem out there. It solves lots and lots of problems, but it will fail. We'll look at an example of when it fails shortly. Okay. So let's say that our quantity of interest is Q, or hopefully a pivotal quantity. It's a function of your data. Let's say it relies on some assumption of what the y's are in terms of the distribution. Then, and unfortunately, the authors include more notation here. It's not I shouldn't say that bad, but they need more notation to say what they want to say. And this Q has a particular distribution. Let's refer to the CDF for Q as G. And they want to specifically point out here that this relies on Y's having a distribution denoted by F. Here's my sample size, and I'm evaluating G at a particular point called little q. Now, what the bootstrap then does is it looks at a very similar quantity, and we put stars in the y's. We now have f hat to worry about, so its distribution is denoted by G f hat for a particular sample size of n, evaluated at q. What we want in a very mathematical sense then is this. The difference between these two CDFs at that same point, we want that distance to get small. Or in other words, the absolute value of the distance being greater than some number epsilon greater than 0. That probability of this happening goes to 0 as n goes to infinity. That's what we want. In other words, we want what we have been calling G hat to be close to G. And this is how we mathematically can actually say closeness. But we like also put G, T, given F here, just to show you all the different little notations that our book uses. Now, for this to work, we need the following things to happen. Again, for the two distributions to be close to one another, we need F hat to converge to F. And I briefly mentioned before, there's something called the Winkel-Cantelli theorem that gives us a very strong sense of how close F hat is to F. Also, obviously, we need some kind of limit to exist. It's no big deal. We need a limit to exist. So as n goes to infinity, it goes someplace and stays there. And last, this is a big one. Small changes in F do not cause large changes in this asymptotic distribution. Okay. Here's an example where the bootstrap fails. I should say, small changes in f do not cause large changes. Think of it also in terms of f hat. Okay, so this is based upon the book, but I've done a lot of extra stuff too. I've actually put it into a numerical sense to help you understand what's going on here. Here's the corresponding program. Suppose theta, suppose f is a uniform zero theta distribution. So notice the maximum value is where your parameter is. In step 883, a very common example that you would work with, or common exercise, is to find the MLE of theta, and ends up being the nth order statistic. Does that look familiar? Some people saying yes. I would assume that those who are not saying yes just don't want to move their head up and down. So what would the parametric bootstrap do? This is kind of interesting. Y star will be distributed uniform zero, your observed nth order statistic. That's where the problem's going to occur. The non-parametric bootstrap, of course, would take resamples the usual way. But the key is to realize the largest possible value that you could have in a resample is your observed nth order statistic. Okay. So that we can actually do a numerical example here. Suppose theta is equal to 1. One can find an asymptotic pivotal statistic. And again, this is, I found it for you. Okay? If you want to know more about how to do this, section 14 of Ferguson 1986. A whole section on what's called extreme value statistics. Q, that's my quantity that I'm going to use, is n times theta minus the nth order statistic divided by theta. In our case, theta is going to be a 1. But no matter what theta is, this distribution is going to converge to exponential 1. So notice it's not normal. This is one of the few places where you don't have an asymptotic normal distribution. Instead, it's actually exponential. Please note that little small error there. So that should be n times 1 minus 2. So because of this, we know what that g with the subscript infinity actually is. We know what that limit should be. It's exponential 1. And in fact, that's where we would like q star to go to as well. As n goes to infinity, we would like it to get there, exponential 1. So there's our q star. Notice how I put this in there. That theta becomes little t. The big T that we had before becomes T star. And there's the theta becomes a T. Note that I don't have a 1 in there for T. Be aware of that. So let's say that I had a sample size of 50. So I'm going to set a C number, use the R unit function to sample from a uniform 0, 1 in a way that you would expect. There's an argument min, an argument max. I calculate T, it's 0.95. Of course, this is yn, or in other words, y50. So let's take some resamples. I'm going to take 2,000 resamples. Make sure I have a large enough R. Set a C number so I can reproduce my resamples. And instead of using the boot function I just cited, let's just use the sample function because this is just a simple example. So I use the sample function the way that we've done in the past. I put the results in a 2,000 by n matrix so that each row is a resample. And then I apply the max function to each row and I put the results into t.star.n part. Let's do some plots. First, I want to do a histogram of these T stars. Remember, T stars equivalent, you could say, the nth order statistic stars, like y sub n within the star. So look on the left-hand side here. This is the distribution of T star. It is very, very discrete. Now, intuitively, hopefully you understand why this occurs. Because we have 50 possible values for the y's. I'm always taking the largest of those values. And let's take a look at, I use the table function here to show you what all the T stars are. Of the 2,000 times that I took a resample, my T star was 0.9519, which is the original value of y sub n, 1,279 times. In other words, that my observed value for the nth order statistic was in a resample 1,279 times. 474 times the n minus 1 order statistic was the largest. And so you can see here what we often refer to this as, we have a very, let's say, non-smooth statistic that we're working with. Very discrete. You could also calculate Q star as well. And I decided to plot then the exponential 1 on it. Ooh, that doesn't look good. Well, you might be saying to yourself, or you might be thinking, well, Chris, of course call me Chris, I'm not going to Chris, you only took a sample size of 50, so maybe the asymptotics aren't kicking in. Well, let's kick it in with n equal 5,000. Do exactly the same stuff. Notice here is y 5,000. And there's the distributions again. Obviously, exponential 1 does not work. So why is this working? Or I'm sorry, why is this not working? Well, it has to do with the fact that we're working with a very non-smooth statistic. What ends up happening then is that small changes, how should I say? Well, why don't we just leave it as it's not a smooth statistic itself, and that our distribution ends up being very discrete for T star. Well, but what would happen then? Sorry, I don't want to get ahead of myself. I should look at the notes. Here's an actual plot of the EDF of all the T stars with the exponential 1 on it, just to emphasize the point that well, basically this G of F hat subscript, G subscript F hat N does not go to G infinity. Well, let's see. I guess what I'm saying is that if you have some kind of distribution for y, we call it f, let's say there's a very small change in, it's better to think about like a discrete random variable. I'm trying to think of a good example. I'm seeing that we're getting closer and closer to 515. I'm like, come on, think under pressure, think under pressure.
We can talk about it later.
Yeah, why don't we just wait? Sorry about that. Are there any other questions that hopefully are take less thought on my part? Okay, why don't we just stop?